So first thing I said was label your equations A, B, and C. That's so everybody knows what we're talking about. Then the step was pick any two equations and eliminate any variable. Any one variable, doesn't matter. So we could pick A and B and try and get rid of the Y, or we could say, let's get rid of the Z. But one of these has to be negative. So what did people use? What did some people use? You pick out Y, Z, X.
So I did A plus B times 2.
To B and got rid of the Y's.
Yes.
Okay.
And then I did something the same for the second one. I did A times 2 plus C.
Yeah, and that would be, that's how I personally would have seen it. But that doesn't mean that if you did it a different way, it doesn't mean you're wrong. It just means you chose a different way. Okay, so I'm going to do it this way. We'll talk about other ways, and I want to show you something on your calculator. So he said he chose A, which is X minus 2Y plus Z equals 3. And then he said 2 times B, because he knew that 2 times that will give me a plus 2Y and they'll drop out. But 2 times B is 4X plus 2Y plus 2Z, maybe I should write equals 4. Add these two together, okay, and we create a new equation called D. So when I add these, I get 5X. My Y's, one's positive, one's negative, so they drop out, plus 3Z equals 7.
Professor, the 4 never changed at the end of 2B?
No, it should be 8.
Should be 8,
Oh,
right?
Thank you. Wow, glad you caught that one.
So
right
that should be
now.
11.
So this should be 11. Thank you, because that would have just really screwed up everything later. Okay, so those were the 2 easy steps. Label as A, B, and C. Pick any 2 and eliminate any variable you want. This one, we dropped the Y value, so we have no Y's. No Y. Okay, that then forces our hand on the next step. We have to use the other equation. In other words, we're forced now to use C, the unused one, and we're forced to drop the Y. So we got to use C and one of these two to drop the Y. And what I heard was, okay, take C, which was 3X plus 4Y plus 3Z equals -1. That's C. And that's already negative, but if we double it, we'll have -4Y and they'll drop out. So we're going to do 2A. Double A, 2 times A will give us 2X minus 4Y plus 2Z equals 6. Okay, giving me 5X. The Y's drop out, plus 5Z equals 5. And we said that new equation that we've created is called E. Now, I need to keep repeating, this is not the only way to attack this problem. These are not the only steps that you can use. These just seem to be, at least to the 2 of us, Mitch and myself, the okay ones. Okay.
Sir, you're cutting out really bad.
I'm cutting out.
Is it
My-
me or is anyone
hear
else
you
experiencing the
It's fine.
professor cutting out?
No, it's fine for me.
I can hear him fine.
Yeah, I
I
can hear
hear
him fine.
fine.
All right,
I'm only getting like every other word you're saying. Maybe I need to
Try-
reset.
log out and come back in, yeah. Okay, so here we go. So any questions about any step I've done so far?
It's still going. Why is it still going?
Well, you
You're
have to
not
exit.
muted.
I don't know, but you're talking to us all, but okay. So now I want to somehow put D and E together, somehow D and E, and eliminate a new variable. D and E and eliminate. Well, I'm going, this is cool because these are both 5x's. So if I could make one of them a negative 5x, doesn't matter which one, I could make one of them a negative 5x and leave the other one a positive 5x. When I add them together, the x's will drop out. So arbitrarily, I'm going to say -1 times d. That's going to give me -5x minus 3z equals -11.
I have a question really quick.
Yeah,
If we're eliminating the y's, for example, I eliminated the x's instead of the y's. Does that matter?
nope,
Okay.
nope. No, it doesn't.
Okay, thanks.
But you bring up a good point, which I'll get to in a minute. Okay, so I have -d, -1 times d, negative, and leave e by itself. So I'll leave it as 5x plus 5z equals 5. Add these, and I get 2z equals -6. Because my x is dropped out like I wanted to. So I get 2z equals -6, divide, z is -3.
Sir, can you let me know whenever you can help me out for a second?
With what? I can't go over this whole thing. It's being taped. Okay.
No, I know that, but I'm so I'm just like I didn't get the same equation you got for your E equation.
Did you have C and 2A? Did you have these two?
I took, what did I do? I took D and C and I added them to create E.
How?
D 5x.
No. Okay, that's you went over this last night. You've got to use your first two steps, use the 3 original problems. The
Right.
only two that you could put together is D and E. D can only go with E. D cannot go with A, B, or C.
Okay, I guess I read that thing. It said using the unused equation, eliminate the same variable. And then it said second step creates a new equation D, third step creates a new equation E. And you're using
And you're
So-
using C and one of the other equations, one of the other
I
original
just
equations.
like to go over it really quick with you and see where I'm going wrong, because even if I go
Okay.
back and when I watch your lectures, I don't know where I'm going wrong.
Okay, hang on. I'll do that after class. We're going to do another one of these.
Okay, thank you.
Okay. Hang on 1 second. Okay, whatever. All right. So I've taken D and E, and those, by the way, are the only ones I can only add D with E. I can't add D with A or C or B or anybody. Just D and E can only be added together. I get this. So now this was, we had some debate last night. We started with A, B, C. We narrowed it down to D and E. And then we finally got Z is -3. We got that answer. Z is -3. So then we use the process called back substitution. It's a fancy word for you plug -3 into either D or E. It doesn't matter which one. You plug Z is -3, plug it into D and E to get an answer. I'm going to plug it into E. Okay. So if I say Z is -3 and I plug it in here, I'm going to take E. I'm going to have 5x plus 5 times -3 equals 5. That's 5x minus 15 equals 5. So that's 5x equals 20, which is x equals 4. So now what I found, if I took Z and plugged it into D and E, I ended up with x equals 4. Well, now I take both of these and plug it into either A, B, or C to get my final answer. And so, and again, it's just a matter of which is easier.
B.
B? Okay. Yeah, because they're all positive. I like that. Don't have to screw around with negatives. So if I go into equation B, B says 2 times x, so that's 2 times 4 plus y, which I don't know yet, plus z, which is -3, is supposed to equal 4. So this is 8 plus y minus 3 equals 4. So this is 5 plus y equals 4. 8 take away 3 is 5. Take away 5 is y is -1. Okay. And then one of the things I said, we always put them as an ordered triple where x comes first, y comes second. So your actual answer is parentheses 4, comma, -1, comma, -3. That would be your answer for this problem. And if you really had no social life and nothing good to do, you take 4, -1, -3, you plug it into here, see if it works for this one, and then you plug it into here, see if it works for this one, and then you plug it into here and see if it works for this one. Okay, and nobody in their right mind will do that. Okay, now what I want to show you now is something. Okay, turn it on. Boom. Let's hope my calculator is working. Clear. Okay. Boom, new share. There we go. Wake up.
The next problem, can you give us a little more time to solve it on our own first?
Yes, I can. Why isn't it coming up? Oh, well, hell. I mean, darn it. Share screen. It should have come up. It is. Ah. Can you guys see my calculator?
Yeah.
Okay.
Yes.
Yay.
Yes.
Okay. Now, this is a 36X Pro. Yay for that. What I want to show you is how to cheat. Okay. So if you pencil, if you, and by the way, some of the other calculators, scientific calculators, have this feature also. You just got to hunt for it. But if you look right here, okay, it says syssolve. That's short for system solver. But it's blue, so you activate it by pressing the second key and then this, right above tan inverse tan, tan -1. So you go second and press syssolve, boom, and it brings up a new screen called System Solver. Okay, and this will solve a 2 by 2 or a 3 by 3, which is what we've been studying. You pay a little bit more money, you can buy a calculator that goes up to 4 by 4 and 5 by 5 and whatever else you want. Okay, but I'm going to choose down here the 3 by 3, hit enter. And what it's asking me, this is a little bit weird. What it's asking me to do is put the coefficients. This first row that you see here, these are all the x's. That's what those represent, all the x rows. Then these are all the y's. These are all the z's, and these are the constants. So it's using a form called a matrix. Okay, you don't need to know that, but that's what it's saying. So this first line is my first equation, but that represents the x, the y, the z. So I had 1x, okay, and then it bounces over, negative 2y. Please remember, okay, to input the negative, where'd it go? Way down at the bottom. Can you guys see it or not?
Yep.
Get this out of the way. This right here is the negative button. It's not the minus button, it's the negative button. So when I want to input a negative 2, okay, I have to hit that button, negative 2. Okay, move it over. Okay, enter.
I can't get it to change that first 0 to a 1. It keeps putting equals 1 below it.
Hit enter. Put a type of 1 and then hit enter.
Oh, I see.
And this was a 1z, so I hit 1, enter. And what did it equal? It equaled 3. So 3, enter. Notice after you entered that, it bounces to the second row. So we had a 2x, so I'm going to go 2, enter, 1y, 1, enter, 1z, 1, enter, and 4. And then last row was 3x, 4y, 3z, negative 1. And again, to do the negative, you got to hit that funny thing down with the parentheses, negative and 1. And after you do all that, it comes down, and when you hit enter after each one, it comes down to solve. So I'm going to hit the solve button. And there I go. It tells me my x was 4, which we figured it out. Oops, sorry. Sorry. Trying to stop it from wiggling. It's on a funky thing. Well, it'll stop in a minute. Arrow down, it's telling me right here, arrow down, so I will. Y is negative 1. Z is negative 3. If I want to go back and solve again, I can do that. If I want to quit, I can do that. If I solve again, notice something. It remembers what our last coefficients were. It remembers what we just entered. Okay. You can just type right over those. So if you have another problem that you want to check, then you just type right over that. Okay, and keep going. All right. This brings up a really, really important issue. You guys have this, most of you, on your calculator. If you look up on Google, if you Google system solver, okay, you'll find something on the computer that will do about the same thing as this, which means that you should get every problem correct. Okay. What that implies then is I'm going to look at your work. I'm going to grade your work. Okay. Not your answer, because your computer will give you the answer. So work on making your work neat, organized. Okay. Several of you asked okay, could I have gotten rid of X's first? Of course you could have. As long as we all got the same answer at the end, you're doing it okay. You're doing fine. But system solver, I'm going to quit for a second. Quit. Okay, go back to second system solver. Where'd it go? There it is. Notice it will also solve a 2x2 system. Okay, it's trying to solve a 2x2 system, which is what we've been working on in this whole course. So really powerful. This is one of the reasons. There's several more that we'll run into over this semester, but this is one of the reasons why I encouraged you to get this calculator, because for like 20 bucks, it does a whole lot. It does a whole lot. Okay, so a couple things I want to get back to my board. Actually, I don't. Okay, let's go here. I want to go back to Canvas modules. And you'll notice can everybody see I'm in Canvas and I'm in module chapter 5. Is everybody with me?
Yes.
Yes.
Okay. Down here, I've made a video of what I just showed you. How to use your TI-36X to solve either a 2x2 or 3x3 system. If you go to YouTube, let's say you've got a Casio, you can search YouTube and come up with how to solve a system of equations on my Casio or whatever calculator you have. And it's pretty much the same thing. Okay, so again, you always now will have the right answer. The job is show me how you got it, and just don't say my calculator told me. Okay, you got to show me your steps. All right. Oops, didn't want to do that. Okay, new share.
Where does it say systems of, wait, go back to your thing. It said, where did it say systems of whatever you had? Mine just says systems of linear equations.
I don't understand. Wait a minute.
I was just trying to pull up what you had up.
Okay, I'm in Canvas.
Right,
Chapter
I went
5.
to Canvas and then chapter 5, but it's like a completely different looking thing than yours. Like I have all the modules here, but there's no sample handouts, videos, or problem solving.
Did you click on them to open them up? They could be closed.
Yeah, so I clicked
you-
on systems of linear equations. I don't have systems of equations and inequalities as one of my modules.
Really?
I have it.
Have what? What I have or what he has?
I have what you have.
Okay, I'm gonna, wow. We're at the end of class, we're gonna have to share screens, Philip, because I have no idea what you're seeing. I really don't. I'm boggled. I don't know. Yeah, I don't know. Hang on a minute. Let me go back. So I don't want that camera. I don't want that camera.
Because you're not in Canvas.
Oh, you were in Mom?
Yeah, I'm in Mom.
Yeah, I was in Canvas. Okay.
I'll show you later.
All right. So what I need us to do, and I'm going to bounce this around.
I have a quick question about showing your work for these problems.
Oh, I shouldn't have erased this. Yeah.
Oh, no, it's okay. So when I was doing this problem, when I was trying to get E, I combined C and A times -3, and that left me with Y equals -1 as my E equation.
Oh, just You got it easy. Yeah, it just happened to skip a step.
Okay, so then it's fine, like if I just show you that I plugged that into everything?
Yeah, that's, you just
Okay.
got dumb, I call that dumb lucky. It happened to skip a couple of steps because it eliminated two variables at one time instead of one variable. No problem. As
Okay.
long as you're showing me your steps, okay, I can follow it then, and that's cool.
Okay, thank
Okay,
you.
Professor,
Yeah.
are we showing our, I'm sorry if we already talked about this before, are we showing our steps like taking pictures of our notebook when we're doing exams and sending it to you? How is it working? Like, or is it in Mom?
okay. In Mom, I don't care what you do. Okay, for the homework in Mom, for the quizzes in Mom, I'm not going to worry about it. For exam number 1, okay, which is coming up in March, okay, a couple weeks from now, I'm going to have a 3x3 system. I guarantee that. Okay, I'm going to have a 3x3 system, and it's going to say solve this and show your steps. And so this is what you would show me. You just write it right on your paper, and then what you're going to do is upload that paper to me with all your work for all of the problems.
Got it.
Okay, that's why we went through that practice thing of practicing to upload, because you're going to have a test. You're going to do it on your own paper, and it's going to be 6, 7, 8 pages long of work. Okay, and you're going to upload all of those into Canvas, and then I'm going to grade it. And for all of those problems, you're going to show me your work, you know, for whatever it took. If it was just a single equation, cool. If it was a graph, cool. If it was a 3x3 system, cool. Just show me your work. That's all.
Okay, cool.
Is that okay? All right. Actually, I was going to go over one more tonight. We don't have time. I want to make sure we get into other stuff. So I'm going to wait. I wanted to do one more. We'll pick it up tomorrow night and see how we do. But you got tons and tons of questions in Mom, not tons. You got 5 or 6 of them for practice. I think I eliminated the word problem, the 3x3 word problem. Has anybody been into chapter 5 on Mom and seen that yet? I think Hamida asked me. Wasn't it Hamida? Did you ask me about the word problem? Or was that
No,
Connie?
that wasn't me.
That was
Okay,
me.
well, okay. Yeah, I believe, thank you for the heads up. I believe I eliminated that word problem. So the only problems in chapter 5 are just systems of equations that you have to solve, not word problems. Okay, still, I want to go over what we did last night. One more time, we introduced one more new thing. Then we'll get to new junk. Please keep in mind, I'm going to erase this, but tomorrow night's our chapter 4 quiz. Okay. The next thing I want you to do, and I'll give you a few minutes to work on this, is I want you to graph this problem. X plus 4y is greater than or equal to 10, and 3x minus 2y is less than 12. I'll give you a hint. When you're graphing with an inequality, it means eventually you're going to be shading. So you want to graph these and then shade. Okay, so give you about 5 minutes. Okay, so admittedly, last night I went through this really quick right near the end of class. So what we said was when we're going to graph this, and this is back to chapter 4, this is stuff you're going to get on tomorrow night's quiz. To graph an inequality, you pretend that it's an equality and you graph it any way you want. Personally, I have a bias towards building a table, but if you wanted to use slope intercept, that's cool. I don't care. Okay, so here's first problem. Okay, I put an equal sign there. I plugged in x is 0 and got y is 2.5. I plugged in y is 0 and got x is 10. So if I come over here on this graph, when x is 0, y is 2.5. Okay, that's 2.5. And when x is 10, I'll get out of the way in a second. Y is 0. So from this information, I got these two intercepts. Now I have to go back and I have to look at the problem. I have to decide, oh, it's greater than or equal to. That tells me I'm going to use a solid line. Whoops, okay, there's 10. I cheated. Okay, I'm going to use a solid line. Okay, so let me make a note of that. It's going to be a solid. Okay, now the other thing I have to do with this is I've got to decide where am I going to shade.
Can I interrupt you real fast?
Yep.
How did you get the 10/4 into 2.5?
Come on, Philip. 10 divided by 4 is 5 divided by 2. You reduce it.
Yeah, I got the 5/2.
That means 2 goes into 5 2 times the remainder 1. That's 2.5. That's changing a fraction. If you had 7/4, that goes 1 3/4 times. 4 goes into 7 one time with 3 left over. That's just changing mixed numbers or improper numbers into mixed numbers.
Sorry about that. My brain is wonky with fractions.
Okay, but your calculator, you can have 2.5. Take 10 divided by 4 and your calculator still gives you 2.5. That's okay. I don't care if you use fractions or decimals. Doesn't matter. So now we have to decide where to shade. Unfortunately, the way this problem is written, there's no shortcut to it. I've talked about a shortcut. This particular problem doesn't have a shortcut. So to figure out where to shade, okay, where to shade, we pick a test point. Generally, because we're lazy, we pick 0, 0 as our test point, okay? All we care about the test point is it's not on the line we're testing. That's the only thing that matters, is it's not on the line. You could pick any other point you wanted, okay, up here. As long as it's not on line, it's a good test point. But we're lazy. So we take the test point, we plug it into the original problem, okay, which gives me x is 0 plus 4 times 0 is greater than or equal to 10. Well, that becomes 0. 4 plus 0 is 0 is greater than 10. That means false. Now, there was some discussion last night. Okay, here's our test point. This is our test point. Our test point for the black line was false. That means everything down below this is false. So where's truth? Above it. So now this is how I do it, and I'm really different than the rest of the world. I put little notes over here. I say on this one, I'm going to use a solid line and I'm going to shade above it. But I'm not going to shade right now. I'm just making notes to myself. If you did this in high school, they had you shade right now. Okay, we don't have to do that. So are you guys, I haven't shaded yet, but is everybody pretty much happy with A, your graph looks something like that. It was a solid line, and by one way or another, you figured out that you have to shade above it. Is everybody happy with that?
I'm happy with that.
Okay. All right. So now we move to number 2. And again, for number 2, we pretend 3x minus 2y equals 12. Again, my bias says go to a table. When x is 0, I get negative 2y equals 12. Divide by 2, 12 divided by negative 2 is negative 6. Okay, plug in y is 0. I get 3x minus 0 is 12. That makes 3x is 12. That makes x is 4. So I'm going to say 0, negative 6. 1, 2, 6. That's 0, negative 6 right there. And 4, 0 is right there. Okay, so now I'm thinking for this line, I can see where the line's supposed to go between that point and that point. But I also know that this is going to be dotted. So I make little notes to myself, okay, over here. So it's going to be dotted. Any questions about why it's dotted? Are you guys all okay for dotted versus solid? Okay. And now I want to figure out where to shade. Again, you can't use the shortcut. Okay, the test point is easier. So we're going to test again. This time we're going to test 0, 0, but this time it's relative to the red line. Okay, so I'm going to test 0, 0. And I'm going to have 3 times 0 minus 2 times 0 is less than 12. That's 0 minus 0. That's 0 is less than 12. That is true. Okay. So wait, relative to the red line, the test point is true. That means relative to the red line, above is where I'm going to shade. We always shade towards the truth. So we're going to go above. Okay. So now my final answer, I need to shade. I need to shade above the black line and above the red line. I need to shade the region. Here, there's 4 regions. I need, which one is above the black and above the red line simultaneously? And it would be this region up here. And so personally, that's all you need to shade. Just kind of shade that in and I'm happy. It makes for a neater answer than having shading for the black line, shading for the red, and overlap. If that's the way you learned it if you've taken this course before a long time ago, that's cool. I can go with that. But I just find it cleaner for me personally to make these little notes to myself. Okay, and then come back and finish it off with the shading up there. So,
Excuse me, sir.
Yeah.
For the second equation, is it okay if we just move it to make it equals y equals?
Oh, yeah.
And put it in y-intercept form?
Yeah. Yes, you can. And the reason that's okay, well, actually, hang on. Yes. In a single word, yes, but you need to be careful. 3x minus 2y is less than 12. Take the 3x over. That's what you're talking about.
Yes.
Come on. Minus 2y is less than negative 3x plus 12. But this is what you need to be careful about. When you divide by negative 2, okay, to get the y alone, what else do you have to do?
Flip the sign, right?
Flip it, right. And that's 3x, so minus 6. So as long as you remember that, then that's cool. Okay,
Gotcha.
That's fine. That I'm really happy. Remember now, okay, you guys, you guys follow the question? He wanted to change this, and instead of using a table of values, he wanted to put it in the slope intercept form. Okay, but you got to remember that when you divide an inequality by a negative number, you got to flip that inequality symbol. But now you can use the shortcut. Remember, if it's in slope intercept form, then the symbol tells you which way to shade. Greater than means bigger, means above. So that would be shade above, which is what we did. So, okay, people always ask me a question, they want a yes and no answer, and I can't do it. I've got to give you a long-winded, boring answer. But the bottom line is that would be perfect, 100% credit, whichever way you did it.
Thank you.
Yep. Any questions on that one? We covered that rather quickly last night. Okay.
I have
From
questions, but I'm gonna
yeah.
save them for the end.
Okay. From my perspective, all this is what we did in chapter 4, which is going to be on tomorrow night's quiz on chapter 4, but now it's putting two graphs at the same time. That's all we're doing. Okay. The last thing I did, all the details. Yeah, sure. Okay. Where am I going? Close the chat. Close that. I want to go over to here. I showed you last night. Wake up. I showed you this thing. It's called desmos.com. Okay. It's free. Some teachers like this so much that they're actually teaching their entire class with this. I don't know how, but they are. So you click on the thing in the center, and our first equation was x plus 4y greater than or equal to 10. X plus 4y. You hit the greater than symbol, and then you hit the equal. That's how you get greater than equal to, and you get 10. So it graphed a line. Is everybody seeing my Desmos?
Yep.
Okay, I just need to make sure I don't trust technology, but whatever. So again, that's the first line here. Okay, and we said shade above it, and that's what it's trying to tell me. And notice it's a solid line. Then you come down to equation number 2, okay, which was 3x minus 2y. 3x minus 2y, y is less than 12. Okay, and again, it graphed it. Notice it's got a dotted line. Okay, and it's kind of hard to see the scale. You can change it down a little bit over here with the pluses and minuses, but you can see the intercepts of 0, -6. Isn't that nice that it shows you what those intercepts were? Okay, that. Oh, look at that. It even shows you where they intersect. Not very nice points, but it shows you points of intersection. Okay, so it's pretty cool. We'll go back up here to this one. We can find an x-intercept. I mean, a y-intercept. We can find an x-intercept. Okay, and you can put as many things on this graph as you want. Notice I shrunk my scale by pushing this zoom in and zoom out. There's other things you can do, but just to keep it basic, you have this as a great, great tool to help you all semester long. So again, this is why you don't need to go purchase a $120 calculator when this is free. Okay. So we are now, why can't I see it? There it is, new share. I don't want to see my calculator anymore. Come on. Ah, there we go. All right, so those two problems that we just spent the last hour on, the 3x3 system and this graphing, that's the end of chapter 5. That's it. Okay. We now,
Didn't you say we were gonna do another one of those problems?
yeah, but I spent too much time on the first one. I'll put what I was going to do it tomorrow morning or tomorrow at the start of class. I need to push off and to get into chapter 6 right now. Okay. So that's what I'm going to do. I always have these grandiose ideas. I want to do this, I want to do this, I want to do this. And we always run out of time, mostly because I talk too much.
I just want to say really quick that the chapter notes that are in Canvas, Philip, they might help you. They have helped me a lot. I think they're Angelica's notes. I think that's what they're under.
And
Yeah.
Angeline,
Going
yeah.
over-
Yeah.
I've been going over the notes online and rewatching the lectures, and I'm still doing the same things wrong. I just really need someone to work with me through a problem.
Okay, have you gotten together? I mean, I'll be happy to do it after class, or we can do it at
That would be
office
perfect.
hours. Or actually, have you been to Anne's tutoring thing? Because she doesn't have a lot of people there and is able to give you a whole bunch of time. Okay, when she, I think
I've been
she's
to the
tutoring.
tutoring.
Okay, so we can do that, but we can hook up after class tonight also when we finish.
Thank
Okay,
you.
We'll work through these. Okay. All right. So we're now going to start. Yeah, I told you Angeline's notes were just awesome. You know, I still haven't figured out how she got them. She was using WhatsApp, and I still haven't figured out how she got her notes out of WhatsApp into my Canvas, but she managed to do it somehow. I don't care if she got it. So now we're going to start chapter 6. Chapter 6 is all about, well, polynomials. Okay, polynomials. In chapter 6.1, okay, there's a whole bunch of vocabulary that I'm not going to go over right now. Okay, you can read it. You guys have all said the videos and Angeline's notes help you. Remember, in each homework assignment, there's a link to a textbook, which will help you pick up the vocabulary also. What I do want to talk about in 6.1 is adding or subtracting polynomials. Well, okay, first off, what the heck is a polynomial? A polynomial is something like that. It's a bunch of terms. Each one of these things is called a term. A polynomial is a bunch of terms, okay, that are linked together in some way. So this is called a trinomial because it has 3 terms. Tri means 3. When we add it with another polynomial, 5x minus 7y minus 6, okay, that's a different polynomial. Again, because it has 3 terms, it's trinomial. However, when we add or subtract polynomials, we add or subtract the coefficient, ooh, here we go, vocabulary, of like terms. Okay, when we add or subtract the coefficient of the like terms. Okay, so now we need to define that vocabulary. Coefficient means the number in front of the variable. So on this problem, the coefficient is a 2. Excuse me, I should be more clear. The coefficient of the x is a 2. On this problem, the coefficient of the x is a 5. So the coefficient is the number in front of the variable. Like terms, most of you know this because we've been doing it for most of the semester already, means they have to have the same variable. So when we say I want to add the 2x and the 5x, because those are like terms. Okay, listen to me carefully. Technically, what you're supposed to add is the 2 plus 5 x's and get 7x. Nobody does that. This is technically correct. When we say add like terms, what we mean is add the coefficient, keep the x. That's what we did here. We added the coefficient and just stuck the x on the end. Okay, most everybody just gets to that answer. They just say, okay, I have 7 x's. Okay, and then we do the same thing with the y's. I have 2y added with a negative 7y. So technically, you're saying 2 plus negative 7 of the y's, that's negative 5y minus 5y. Again, I firmly believe that everybody should be able to, or everybody can, add 2y, take away 7y is negative 5y, and you can do that in your head, and you don't need any of this technical crap. Okay, but I'm showing you what's technically correct. And then plus 3, these are like terms, so we have 3 plus a negative 6 is negative 3, and that would be the answer. Okay, those are adding or subtracting. We add or subtract like terms. Okay, that should be pretty straightforward. Now, I need to erase down here my technical stuff. Is that okay?
Yep.
So, okay, subtraction gets
Right,
a
one
little bit,
question.
yeah.
Are you ever gonna have a polynomial with different numbers of variables on each side?
Yep.
Okay.
It doesn't matter. That won't change anything. Let's say,
Like if
okay,
I were to
let's-
get rid of the 3, it would just be a negative 6 on the end of that, right?
Yeah. Let's say we have 7x minus 5y squared plus 7, okay, minus 3x plus 5, no, plus 8y squared, like that. So now, this is called a trinomial because it's got 3 terms. Trinomial. And this is a binomial. Okay. A trinomial has 3 parts to it. A binomial has 2 parts to it. Just throwing in some vocabulary there for you to play with. This one, subtraction, is really, really tricky. Okay, it adds an extra step. Some of you can do this in your head. Some of you can't. Okay, whichever way you do it, as long as you get the right answer, I don't really care. What happens is this subtraction symbol actually distributes in. Now, we've done this with equations back in chapter 2. Okay, so we would rewrite this problem as 7x minus 5y squared plus 7 minus 3x minus 8y squared. So you would rewrite the problem distributing the minus sign through there, which changes those to their opposites.
Yeah, you're
Now-
pretending like it's -1, right?
Yeah, that's exactly right.
Makes
You're
sense.
thinking of it as -1, you're distributing at a -1. So now, like terms. Here we go. I'll skip a step now. We have 7x's minus 3x's. 7 minus 3 is 4. So we end up with 4x's. 4x's. Okay. Then we look for more like terms. Y's and y's. Y squareds, I'm sorry, and y squareds. More like terms. Okay. But this time I have minus 5, minus 8. Okay. So I have minus 13 of the y squared. So remember, when you add or subtract polynomials, you only add or subtract the coefficient and you just stick the variable on it. Okay. Last thing, 7. Well, 7 is a normal number. So the only thing 7 can add or subtract with is another normal number. There aren't any more. So I just stick the 7 up here. And that's my answer. Okay. Again, you can't go further because we say these are not like terms. Nobody can add together. Like terms are defined by their variables. If the variables aren't exactly the same, you can't do nothing with it. That's bad English, but you guys get the point. Okay. One more example, then we'll move on to more funner stuff. Okay. I kind of want to erase this. Can I erase what I have up here right now?
Yeah.
Yes.
Everybody's okay? Okay. All right. So this next one is easy, but it's got a subtle little mistake in here. Not mistake, it's a subtle place that students make mistakes. Typically, we get in algebra, you guys have seen this, 5x squared minus 2x plus 9 plus 3x squared minus 7x minus 16, something like that. We do a lot of things in algebra because we have no imagination, so we always use x's. Okay, why? Because we're stupid. So when we add these, again, like terms, we get 8x squared. Okay. More like terms, 2x negative 7x is minus 5x. And 9 take away 16 is minus 7. Okay. Now, here's what some students do. They go, oh, those are x's. Okay, so I can put those together and get something like 8 take away 5 is something like 3x minus 7. Wrong. You can't do that. These are not like terms. Okay, they have to have the same variable and it's got to be exactly the same variable. These are related to each other. They're like cousins. Okay, but you can't put them together, at least not legally, at least not in California, maybe Mississippi. Never mind, that's a bad joke. Okay, you can't put these two together. They're not like terms. Okay, so that is your only final answer. All right, pretty much that's it for chapter 6.1. Okay, or 6.2, I'm sorry, that's what that was. And 6.1, okay. So pretty much, are we okay with that? 6.1? There is some vocabulary. I've tried to talk about some of it. You'll find more in MOM, more reading, more in the videos, but it's pretty much there. Okay, moving on. New stuff. 6.2. Where do I want to go to? 2. This is going to get a little bit hairy, so hang with me. Chapter 6.2, these are going to be our rules of exponents. Okay, rules. And I can't stress enough that what we do now will then come back and bite us big time in chapter 10. We're going to introduce exponents, and you're going to think it's overkill. Okay, and you're going to get kind of lost in it, so hang in there. But then we're going to come back in chapter 10, and you're going to wish you had done better in these exponents. Okay, math always does that. They introduce something, you go, whew, glad we're out of that. And then about 2 chapters later, bam, they hit you again. You go, oh crap, we're back in, and it's worse than it ever was. Okay, this is it. First off, some basics. When we go 3 to the 4th power, 3 to the 4th power, we do need some vocabulary. 3 is called the base. And 4 is either called the power or the exponent. That's the vocabulary. What does it mean? It means 3 times 3 times 3 times 3. Okay, a total of 4 times. There's 4 of these. 4 of these. So an exponent is a fancy way of saying repeated multiplication by the same number. So bottom line, when you get to exponents, it really is rules for multiplication. That's what they mean. Exponents, rules for multiplication. Okay. In the end, this comes up to 81, which I don't care about. Okay, your calculator will do that. But I need to talk about the basic rules. 3 is the base. 4 is either called the exponent or the power. Okay. It means we have whatever the 4 is, 4 of these thingies, 4 of these base numbers, and then you multiply them together. But the subtlety is that exponentiation, the use of exponents, really and truly means multiplication by the same number. So, some basic rules, and then we'll get into some tricky rules. Okay. First, some basic stuff, very basic. Okay. Any number to the 1st power is itself. Any number, A, raised to the 1st power is always itself. Okay. So for example, if we have, 7 to the 1st power, it's worth 7. Okay. This is called a bi-directional rule. As a matter of fact, all of our rules in math are bidirectional, which means usually you see it A to the 1st equals A, but it could go the other way. If you have A, you could say, oh, there's an invisible 1 on top. Okay, recall when we write X, how many invisible numbers are there around X? Well, there's 1 times X. Remember, there's a 1 in front of it. Oh, there's also a 1 underneath it. Now, there's a 1 power. So every time we write X, there's all these invisible things that go along with X that the student is expected to see. My job is to keep repeating this until you do see it, until you're so sick of me, you don't want to hear it anymore. Okay, so first basic rule, anything to the first power is itself. Second basic rule, anything to the 0 power is 1. I will explain this later. Okay, right now, it's not good teaching, it's horrible, but this is just a sort of a shut up and memorize. Anything to the 0 power is worth 1. Okay, I'll explain why this comes up. So for example, if you have, I don't know, 3 times 4 plus 9, quantity raised to the 0 power times 2. So we have 3 times 4 plus 9, quantity to the 0 power. Then whatever this is, I don't care. It doesn't matter what 3 times 4 plus 9 is. Anything to the 0 power is 1 times this 2 that was out here. Final answer for this particular example is 2. But anything, any quantity raised to the 0 power is automatically 1. You don't even have to do the work. You can just say it's 1. Okay. Just sort of a kind of a minor heads up. I always give a problem something like this. On a test. And I'm going to explain all this to you later. But this is 2 times x to the second times y to the third, the whole quantity to the 3rd power. Okay, times this mess to the 0 power. Well, what happens? This becomes 1. So this effectively drops out of the problem, and yet students will try and do all kinds of crazy stuff with this when actually it's just a 1, and the only part of the problem you have to do is that part of the problem, which I'll explain later, so don't panic. Okay, but you've got to know any quantity to the 0 power is always a 1. Okay, that's some of our very, very basic rules. Basic. Now we're going to get into our more common rules. Okay, only because I'm weird, I'm going to do it backwards. When you look in the book, the rule I'm going to give you is the last rule they teach you. Okay, they teach you in the order of these rules, in the order of easy to difficult. I'm teaching you the rules in the order of how you should do them in a problem. This is kind of like the PEMDAS of exponents. Remember, PEMDAS says, what do you do first? What do you do second? What do you do third? Okay, that's what I'm teaching you. Okay, so the first thing you do is you distribute to remove any parentheses. Let me show you what that looks like. I'm going to do a quickie example. Okay, so suppose you had 2x squared y quantity to the 3rd power. 2x squared y whole quantity to the 3rd power. The first thing you do is you say this is 2 to the 3rd power times x squared to the 3rd power times y to the 3rd power. That's the first thing you do. You distribute that power to everything inside that parentheses. So there's no more parentheses. Okay, notice I wrote timesing there. That's going to be kind of important, because remember, mathematicians imply multiplication. We don't like to write it because we're lazy. But as a student, maybe writing that multiplication symbol might help you a little bit. All right, that's our first rule: distribute to remove parentheses. Our second rule, okay, is if you have a power raised to another power, okay, a power to a power, you're going to multiply the powers, but you're going to keep the base number. Where are my pins all day? Okay. So first thing, you look for parentheses and you get rid of them if you can by distributing. Second thing, you look for a power raised to a power. Like this is a power raised to a power. And when you see that, a power raised to a power, you multiply the powers, but you keep the base number. So I'm going to do two things. First off, this is 8 times x to the 6 times y to the third. Okay. Always, if you could do the just basic arithmetic, 2 to the third power, you do it. 2 to the third power is 8. 2 times 2 times 2. Or your calculator will do that for you. But the key I'm talking here is if you have a power raised to a power raised to a power, you multiply the two powers together, okay, and you keep whatever the base number is. So I have 2 times 3 was 6, keep the x. Okay. Third rule. If you have same base and they're multiplying, you're going to add the powers, but you're going to keep the base.
Can
Okay.
you move the light a little bit? It's like right on what you're writing. The glare.
Yeah. You know, the problem with that is the glare is coming from the camera itself.
Yeah, can you write it down?
How about I'll come up here? Third rule. Actually, let's change it to rule 3A. Okay. If you have same base multiplying, you add the powers and you keep the base. Okay, there's a rule 3B, which I'll get to in a second, but this example I've given you here isn't good enough anymore. So first, get rid of parentheses. Second, look for power raised to a power. Third, look for the same bases that are multiplying. If we look at this problem right here, the bases are x and y. They're not the same. so rule 3 doesn't apply. It's got to be if they were the same basis. Now I'll do an example in just a second. So the final answer for this example I gave you was this. If you had 2x squared y quantity to the third power, first you distribute the power to everything, and even if it looks weird, you don't worry about it. Distribute the power to every piece inside. Then you look for power raised to a power, you multiply them and keep the base. Then you look for same bases. Same bases, there aren't any, so we're done. Now I'm going to give you a much more complicated problem in a second. Okay, and I'm going to add a rule 3b in a second. Okay, have I lost anybody yet?
Just a quick question. How did you get the 8?
2 to the third. Go off to your scratch paper. 2 to the third means 2 times 2 times 2. 2 times 2 is 4, times 2 is 8.
Got it. Thank you.
Okay. What's the common one everybody puts as 2 to the third and gets it wrong?
6.
6.
27.
No, that's 3 to the third. I've never heard of anybody get it wrong, but Richard, you're the first. Good for you. Okay. Yeah, go ahead.
With the second point, we are supposed to multiply the powers. So why didn't we keep the 2 power?
Those are 2 different things. This is just 2 to the third power.
Mhm.
This is just arithmetic. Okay, there's no rules for this. Just says go off and do 2 to the third power. This is your exponent rule right here.
Okay.
Power to a power. That's what that rule said. Okay, or not?
No. So
No.
why didn't we leave the 2 to the power 3 then, but we made it 8?
Because we always want to simplify. I mean, what's easier to write, 2 to the third or 8?
8 though, yeah.
That's it. So if you can do arithmetic, which is what that is, you always do that. Forget all these other rules. It doesn't matter. If you can do the arithmetic, 2 to the third power, you do it.
Okay.
And these rules that I'm giving you, all this junk, is only when we have like X's and Y's and all this other stuff.
Mhm. Yeah, I get it.
Okay. Anybody else? I need to erase for a second. Okay. So let's do a more complicated problem. Okay. So more complicated. Okay. 3x to the 4th, y to the 5th, quantity to the 3rd. Here you go, Richard. This is for you. Times 2x to the 3rd, y to the 7th. I'm going to walk you through it just to make sure we're all doing this right. And then I'll put up a couple more problems for you to practice on. All right. Rule number 1, distribute to remove the parentheses. So this is going to be 3 to the 3rd, x to the 4th to the 3rd, y to the 5th to the 3rd. Nothing here, so I just say times 2 times x to the 3rd times y to the 7th.
Did you mean to not put a times marker in between x and y, or can we just put them?
No, I screwed up. I didn't mean to do that. You don't have to at all. You don't have to, as long as you remember that. I'm putting them there because over the years, I figured out that students don't understand that that's multiplication, not addition, not subtraction, not division. So I put it there to emphasize the multiplication. Okay, next step. Okay, step number 1, distribute to remove get rid of the parentheses. Next step, look for a power raised to a power. Right there and right there. That's a power raised to a power. The rule said multiply the powers, but keep the base. Multiply the powers, but keep the base. At the same time, I'm going to do arithmetic. 3 to the third is 27 times x to the 12 times y to the 15. When you see a power raised to a power, you multiply the powers, 4 times 3 is 12, but you keep the base number. Power to a power, 5 times 3 is 15, keep the base number. This 2x to the third, y to the 7 isn't important anymore, or hasn't been important yet. It's going to be super important now. Okay. So, Rule 3a says if I have the same base and if they're multiplying, then I add their powers but keep the base. So, I'm going to put an extra step in here. I'm going to put an extra step so you can see what I'm doing. First off, I always do arithmetic, 27 times 2. I get that. That'll become 54 in a minute. That's arithmetic, 27 times 2, whatever. I see x, they're multiplying together. So I add the powers. That's what that said. If I have the same base and they're multiplying, I add the powers but keep the base. So x and x were the same base number. They're multiplying, so I add the powers, keep the x. But the same thing happens with the y and y. So I keep the base, add the powers. Okay, final answer, 27 times the 2 was 54. X to the 15, y to the 22. And you can't go any further because nobody's got like bases. You're done. So, questions?
So after adding the powers,
Wait a minute. Who is that? After you adding the powers, 12 plus 3 is 15?
no, before that. Yeah, so the next one, it's kind of like grouping like terms, or
In a way, yes.
okay.
In a way, because you're looking for same base. You said like terms, I'm saying same base.
Oh, same base.
Same base. So the x's were the same base. So we keep the base number, but we add the powers. Keep the base number, y, add their powers. And again, the 27 and the 2, 27 times 2, that's just arithmetic. That's just plain old ordinary arithmetic. So we just
Wouldn't
do
it be 15x? Or you're just putting x to the 15. Never mind. Sorry, you're good.
Yeah. Keep the base number. You got to keep base and powers, make sure you know who's what. All right.
Professor, quick question.
Yes, sir.
For me, it's going back many years back. Is it different or easier, or can it be possible to write the second trinomial, whatever you call it, underneath the other one?
Below
No,
it, yeah.
because that
Below
would be division.
Oh, okay.
And that's a different set of rules, which I'll get to, but not now. That would be division. Is it possible? Yeah, but only if I wrote it that way.
Okay, we will be confused. I got it.
Okay.
Thank you.
Yeah, this is multiplication. All right. Let's try one on you guys on your own, okay? 4x to the third, y quantity to the second times pin that's dying 3x to the second, y to the fourth to the third. Okay, so 4x to the third, y quantity to the second power, new quantity times 3x to the second, y to the fourth, whole quantity to the third power. Give you a couple of minutes to try that. Okay, so we got to go. Step number 1, distribute. So this is going to be 4 to the second times x to the third to the second times y to the second. This is a distribute times 3 to the third times x to the second to the third times y to the fourth to the third. That would be my first step. Distribute the power and get rid of all the parentheses. Okay. Next step was if there's a power to a power, you multiply the powers, but keep the base. And simultaneously do some arithmetic. You can always do arithmetic. So 4 to the second power is 16. You can always throw that in. We don't need a rule for that. Just do the arithmetic. But this is a power raised to a power. So that should become x to the 6th. Power raised to the power, you multiply the powers, but keep the base number, whatever the base thing was. The y to the second stays here. Okay. 3 to the third is 27. That's arithmetic. Power raised to a power, you multiply. This is x to the 6th again. And this will become y to the 12th. That would be my next step. So always arithmetic. 4 to the second is 16, 3 to the third is 27. But the rule for weird exponents is if you have a power to a power, you multiply the powers, keep the base. And the question was, what do you do with y to the second? Nothing, because it's not a power to a power. You're doing the rules in order. Okay. Third one, if they have the same base and they're multiplying, then you add their powers and you keep their base. So again, some arithmetic. We're still going to do off on my calculator 16 times 27, whatever that is. I think it's 432.
Yes.
Okay, that's the 432 part. But with my x's, my same base, I'm going to have x, same base, add their powers, 6 plus 6, okay, to x. My y's, okay, are going to be 2 plus 12. So arithmetic, 16 times 27. Keep the base numbers x, add their powers, 6 and 6. Y's, keep the base number y, add their powers, 12 and 2. Final answer, 432, x to the 12, y to the 14. And that is just simply your final answer. Want to try one more of those before we get to nasty?
Yes, please.
Okay. Is that okay? Because I need to erase some of this. Are we okay? I'm trying to follow those rules as I gave them to you. The only one that's fouling you up is when I do arithmetic, just basic 4 to the second, 3 to the third, and then multiply those together. That's just arithmetic. You do that anytime you want. Okay, last one of these, and then we'll get weird. Okay, let's see what I have. Negative 5 x to the 4th, y to the 7, z to the 3rd, quantity to the 3rd, times x, my pen is dying, to the 7, y to the 3rd, quantity to the 4th. So if you can't read, I think you can. The first quantity was negative 5, x to the 4th, y to the 7, z to the 3rd, whole quantity to the 3rd power, times quantity x to the 7, y to the 3rd, quantity to the 4th power. So give that one a try. So speeding up a little bit, this is negative 5, quantity to the 3rd power. Remember, the 3 goes to the negative and the 5, the negative 5. That's the number. So all of that is being raised. This is x to the 4th to the 3rd. This is y to the 7 to the 3rd. This is z to the 3rd to the 3rd. This is x to the 7 to the 4th. And this is y to the 3rd to the 4th. Okay, again, this is negative 125, and that's just using your calculator and arithmetic. Power raised to a power, follow, again, guys, I can't stress enough, follow those steps in order. You can't skip around. You can't do them out of order. You'll get screwed up. Maybe once in a while you get it right. Most of the time you'll get it wrong. Follow those first, second, third steps. So this will be x to the 12, y to the 21, z to the 9. This will be x to the 28, y to the 12. Okay. Combine, look for same bases. So negative 125 just comes down. I have x to the 12 plus 28, y to the 21 plus 12, oops, and z to the 9 doesn't get along with anybody. Remember, these are all multiplying together. So now shove it all together, final answer, negative 125, x to the 40, y to the 33, z to the 9. Doing okay?
Yes.
Okay. Now it's super, super important, guys, that you recognize that I will accept your skipping steps. I know some of you, based upon comments I've heard previously, are remembering this course. Okay. And you can take steps. That's fine. You can skip a lot of steps. A lot of people could go from, like in this problem, from here to here in your head. Cool. Just don't screw up. I'm showing you all of the steps that you should be thinking about. If you can do some of these in your head, great, wonderful. Okay, If you can't, write them down like I just did there. All right. These to complicate your life a little bit more. Yay. Just what you need. Hang on, I'm trying to get more ink in my pen. Okay. I put up here Rule 3A, which is the same base and they're multiplying. Okay, add the powers, keep the base. That's kind of what we did here, going from here to here. We looked at the x's, we keep the x, we added the powers. Or over here, going from this step down to this step, we keep the x, added their powers. But what if they're dividing? Okay, what if they're dividing? So, erase. Okay. We're going to talk about a trick shortcut. I'm going to avoid rules now, but what if they're the same base, but they're dividing? You're going to keep the base and you're going to cancel powers. Now, this is not the official rule, not by a long shot, but it's the rule that's easiest for students to use. And after a lot of discussion with a lot of instructors, they like this first, and then eventually they'll show you the real rule. Let me show you what I'm talking about here. What if you had 8x to the 5th, y to the 7 divided by, I don't know, 12 x to the 3rd, y to the 9th. Okay. What you want to do is you want to think of this as 8 over 12, x to the 5 over x to the 3, y to the 7 over y to the 9. Now, this is important. You want to think of this. You do not have to write it like I'm doing unless it helps you. But look what I've done. I've segregated numbers with numbers, x's with x's, y's with y's. And each one can be reduced, like 8/12. That ultimately reduces down to 2 over 3. 8 over 12, okay, reduces down to 2 over 3 because you can divide by 4. Now here's the tricky part. Here's the new stuff. With my x's, okay, think about this. I have 5 x's on top and 3 x's on bottom. 5 x's on top, 3 x's on bottom. Well, doesn't it kind of make sense to think that a lot of these cancel each other out? There's a lot of canceling. And so you're left with, so we have 2 over 3, you're left with an x squared on top. You're left with 2 x's on top. Okay. What about your y's? Well, why did I pick such damn big numbers? That's like y on top, 7 of them. And y, how many is that? 1, 2, 4, 5, 6, 7, 8, 9. Yeah. Okay. So again, That's what y to the 7th really means. That's what y to the 9 really means. It means a whole bunch of them. But look at this. These cancel, and these cancel, and these cancel, and these cancel. In fact, everybody and their mother cancels except those two. So what are you left with? Y to the 2nd on bottom, and you're done. That's what that rule says. If they're the same base but dividing, if they're the same base but dividing, you keep the base and you cancel the powers. You keep the base, cancel the powers. So I keep the x, but I say, oh, look, there's canceling. 5 on top, 3 on bottom. After they cancel, there's more x's on top. There's 2 on top. Look at the y values. There's more y's on the bottom over here. So after they do all their canceling, there's still going to be more y's on the bottom. We just cancel out all the extras crud. That's all that says. Okay. Again, I think that after a little bit of practice, a majority of the class can do this whole problem in your head. I'm trying to show you the thought process that goes into what you're doing. You're reducing number with number, x with x, y with y. Okay.
Do you mind if we do one with an uneven amount of variables on top and bottom?
Sure, like throw a
Will
z
we-
in.
Will we run into that or something?
What do you mean by uneven?
So if I had like an extra z squared on top and not
Oh,
on the
sure. Yeah, then I'll do one, but the bottom line is then it doesn't cancel with anybody.
So z would just
It just
remain on top
or on bottom or wherever it was. Yeah,
wherever it's located. Okay.
Yeah.
I think that makes sense.
yeah. Please notice something before we do another one. You got to pay attention, and this is important in life too, to who's on top. Wait a minute, who's bigger on? No, that's still wrong. Okay, never mind. Okay, who's bigger? Because after these cancel, if we have more x's on top, even if they reduce, we're still going to have x's on top. But over here, if you have more y's on bottom, even after they reduce, we're still going to have y's on the bottom. So you need to pay attention to, where do I have the bigger number? It's still going to be bigger in your answer. All right,
Professor,
let's-
what if there were more X's on top and more Y's on top as far
then
as canceling out?
that's cool. Boom, boom, boom. Okay.
Can we just do another one?
Yeah. Yeah. I'm trying
Just
to
one
think.
more time.
Okay. The answer to the question about then there's none on bottom. That's just
You're
the
right.
answer.
I was just trying to, I was wondering, I mean, is the X on top because of that and the Y's on the bottom because of that? Is that
Yeah.
why?
And if you had more on top of everything, okay. I was going to make a joke about Dolly Parton, but no. Then you just left with more on top and none on the bottom, and that's okay. Okay, let me do a problem. Okay. So what would this come out to be? Well, whatever. This was 2/3. This was 2x squared over 3y squared, and we were done. Okay. So new problem. Negative 15 x to the 9 y to the 3rd over 20 x to the 10 y to the 5. Yeah, that'll do it. Give that a try. Okay. So again, I separated numbers with numbers. 15 over 20 are going to reduce. I believe that reduces, if I listen to that, -3 over 4. Okay, 15 over 20 reduces to -3 over 4. Now I'm looking at my x's, and I'm saying I got 9 on top, 10 on bottom. Most of them are going to cancel out, so I have 1 on the bottom. And again, you don't need that 1 anymore, but you have 1 on the bottom, at least for now. My y's, okay, they're going to cancel. I'm going to have 2 y's on the bottom, so I write y squared. Better answer, -3 over 4x y squared, because that first power, again, mathematicians are snobs and they're lazy. Even though that's correct, we don't write it because we want to appear sophisticated. So we just say x instead of x in the first. But that would be the final answer. That's it. You're done.
And you choose the, excuse
Go
me, the
ahead.
bottom, you choose the bottom. So x1 and y2 are at the bottom because,
There was more on the bottom to
Got it.
begin with.
okay.
Okay. Somebody else started to ask a question. How are we doing?
I got it. That makes sense. Thank you.
Oh, okay.
That was good.
Okay. I've got my eye on the clock. We went long last night. I'd like to teach one more thing and then quit. So if you give me about 5 or 6 more minutes, then we're going to be done for the night. So again, we'll keep reviewing this, but we're into chapter 6.1, 6.2 right now. You guys should be able to, like over the weekend, maybe start chapter 6. So I want to introduce a new rule of exponents. Okay. Negative powers or exponents. Okay. And this is not fair. Okay. This is the ultimate in arrogance. From my perspective, it's really simple. However, apparently I don't teach this well because it creates confusion among students. So we'll try it, and I'm expecting a lot of people yelling at me and a lot of people asking questions. Okay. If we get, here's our rule. If we get, let's say, a to a negative power, okay, a raised to a negative power, then this becomes 1 over a raised to the positive power. So in my mind, a negative power means flip, reciprocal. In fact, if you look it up, that's what it means, the reciprocal. A negative power means the reciprocal. Example, if you have a to the -3 power, then that becomes 1 over a to the +3 power. When you flip, the power flips from negative to positive power. But notice it flipped down. It flipped to the denominator.
That doesn't really make sense.
Well, okay, I'm not asking it to make sense. I'll show you where the
I know.
rules came from.
I just confused at where the negative went.
It just went away. The flipping of it used up the negative. The negative means flip. When you flipped it, you've used up the negative part of it.
Okay.
Okay. It's like, well, never mind. I'm gonna come up with some metaphor
Okay.
or something. But no, the act of flipping, okay, uses the negative up. It's just gone anymore. If you unflipped it, then you'd be back to the negative. The act of flipping,
Oh, because it's technically a negative or a -3/1 right now. So
yes,
okay, I get it.
okay. So here's what you see. Let's take x to the -2, y to the 5 over x to the 3, y to the -7. Okay. Again, you should separate mentally, you should separate this. So you got x's and x's, and then you have y's and y's. Okay, but these aren't normal powers, these are negative powers, so they flip. But watch what happens. Does this x to the 3rd, wait a minute, stop. I sound like Willy Wonka. Stop, play back, do it again. Okay. Only negative powers flip. So x to the 3rd doesn't flip. But x to the -2 does flip. And it flips down. Flips over. Over here, y to the 5 is positive. It doesn't flip. But y to the -7 does flip because it's negative. So the only place it can flip is up. And notice when it flips, it turns from negative to positive. So x to the -2 flips down and becomes x to the +2. Y to the -7 flips up and becomes y to the +7.
So
Now,
it depends on where your negatives are.
exactly. That's all it means. Now, there's always these invisible ones there for those of you who are worried about fractions not looking quite right. There's always a 1 there. Okay, so you can still see who's in the fraction and that kind of stuff. So now check it out. What happens is now we're back to this rule. If they're the same base and multiplying, we add the powers and keep the base. So this is going to be 1 over x to the 5th. Add the powers. 3 + 2 is 5. Keep the base. This is going to be y to the 12 over 1. Okay, because they were the same base multiplying, so we add their powers, but keep their base. Now shove all this back together, and the final answer is y to the 12 over x to the 5. And that is your final answer. So what happened? The negative powers flip. If they were in the numerator, the only place they can flip is down. If they were in the denominator, the only place they can flip is up. Negative powers cause you to flip. All right, let's try one more of those and then call it a night. Okay, I'll do this. I'll do it over here.
Who came up with this?
I'll show you tomorrow night where it came from. You make it sound like somebody's out smoking drugs or something like that, and they said, "Oh, let's just make up a rule to screw up everybody." No, actually, there's a really good math reason for this, and it does make sense. And either I'll show you tomorrow night or I'll show you next week. It it really is simple. It's just, okay, here's a bottom line. You asked the question. I won't show you this until next week. But you guys know about the XY axis. This is the X axis. This is the Y axis. Okay, and we use this all the time for graphing. Do you want to know who invented that? A French guy. His name was Rene Descartes. Okay, Decarte. Rene Descartes. And he was a philosopher, a mathematician. He was just all around brilliant. But he was also a gambler. Okay, and oh man, did he like to drink. So one night, after a whole night of debauchery and drinking and whatever, he came into his bedroom, collapsed on the bed, and he wrote this down. Okay, he said he was watching a fly walking across the ceiling of his room. So now he's bombed, he's blitzed, okay, and he's watching this fly, and he thinks to himself, if I had two number line axes, 1, 2, 3, and this is 1, 2, 3. He said, I could describe the fly's position on the ceiling if I took two number line axes and put it up on the ceiling. Then I could tell you the fly is at position 2, 4. Oh no, the fly walked over here at position -5, 7. Okay, so real truth, this guy named Rene Descartes, who was a philosopher and a mathematician and a gambler, and he really liked the ladies and he really liked to drink, was watching a fly walk across the ceiling and decided he wanted to be able to describe the fly's position. So he invented this system, and for the longest time, if you look it up, a lot of people called it the Cartesian coordinate system. Cartesian, based upon his name, Descartes. Okay, the Cartesian coordinate system. Okay, we now just get lazy. We call it the XY coordinate system or something like that, or the rectangular coordinate system. But anyway, so yeah, some of math comes from drugs. I totally agree. Okay, but negative powers doesn't. Negative powers actually comes out of some pretty easy math, which I'll show you later. Okay, more than you wanted to know. I know. Okay, those are the fun things I think of math. Otherwise, it's just boring as all hell. Okay, -6, x to the -2, y to the 15 over let's go 18, x to the -3, y to the -5. Okay. I'm trying to trick you now, but go ahead and do the best you can on this problem. -6, x to the -2, y to the 15 on top. 18, x to the -3, y to the -5 on bottom. Try and simplify it. Okay, here we go. Okay. First
Plus-
off,
Ah,
does the -6 flip?
no.
Why not?
Because it doesn't
On
have power.
exponent.
It's a constant.
Okay, it's a constant. The only thing that flips are negative powers, not negative numbers. Okay, somebody called this a constant. That's a good call. This is just the fraction. This reduces to -1/3. Negative ordinary numbers don't flip. The only thing that flips is negative powers. So you guys as students need to pay attention to these little details. Is it a power? Then it flips. If it's not a power, it doesn't flip. All right, over here, next one. Does x to the -2 flip? Yeah. It becomes x to the +2 on bottom. Does x to the -3 flip?
Yeah.
Yeah, becomes x to the +3 on top. So both of these flipped. Both of these flipped because they were both negative. Okay, let's move to the y's. Does the y to the 15 flip?
No.
No, it stays. Y to the 15 because it's positive. Does the y to the -5 flip? Yep, y to the 5. Okay, and remember, there's always that invisible 1 down there if you need it to. Now, we're down to rule 3. If they're the same base and multiplying, we're going to add the powers. Okay, if they're the same base and dividing, we're going to cancel the powers. Same base divided, cancel the powers. So this is -1/3. Look at my x's, same base dividing, cancel the powers. I got 3 on top, 2 on bottom. What do I have left? Anybody?
1 on top.
X.
An x
X on the
on
top.
top. It's important to specify on top. Okay, because x could be anywhere. What about my y's?
Y20.
Y to 20 on top. Shove it all together. I have -1, x, y to the 20 on top, 3 on bottom. You probably don't need the 1, but I would give you full credit. I'd be excited. Okay, quiz tomorrow night. Yeah, go ahead, ask. But anybody else can check out. I'm sorry. I'll shut up now. Listen.
No, wouldn't you need the -1 up there just because it's negative?
Remember, in math, -1x and -x are the same thing.
Wow.
Those two are the same thing. Because we're lazy, we accept that. Remember, for some reason, we think that that's too much of a burden to write -1. We'd rather write -x. These are the same thing. So we would say a more sophisticated answer would have been -xy² over 3.
And then why did we have the squared instead of 20 for y?
Oh, because I'm an idiot. Thank you.
Oh, you're good.
Okay, I was about to ask the same thing.
Yeah, sorry. No, that was way bad on my part. Okay, again, I started to say I'm done for the night. So those of you who want to go. I want to answer a couple quick questions and then work with Philip. And I will work with Philip. It's okay. Okay. So if you want to check out, you can. Or does anybody want to work with Ann for a second? I can put you into a breakout room.
Be happy to help.
Good night.
All right.
Good night, Professor.
Good night. See you guys tomorrow.
Thank you. Good
Well,
night.
we'll see who's hanging around. Hang around for a couple seconds, Ann. Okay, Philip, what were some of your questions?
Oh yes, could we go through slowly one of those problems with the systems, the 3 systems? With
Sure.
all those equations like D, E, A, B, C.
Yep, we can. Let me see if I can find one. Okay. So here you go. X minus Y plus 3Z equals 2. 4x minus 5y plus, oh God, 14z equals 3. I hope I copied this right, please God. 5x minus 6y plus 19z equals 3. Let me make sure I've copied it right before you get going. Where did I get it? That's not the one I want. Page 299, I got that. Oh, x, y, 3z, 2, 4x minus 5y, 14z, 3, 5x minus 6 plus 19, 3. Yeah, okay. So I've copied it at least correctly. We'll see how we do it. All right, you want to tell me what to do? Oh, wait a minute, hang on. I'm gonna